Hey and welcome back. So today we're going to talk about something called raster interrupts. Now, this is I'm going to be honest, this is a pretty complicated subject. So I'm not going to go into any detail here. So remember what I said at the beginning of this course. I'm not going to overwhelm you with details or anything like that. Now, especially when we're dealing with something like this. This is super technical. So, for example, when we're moving sprites around on the screen, moving a sprite left and right, up and down, or when we're changing the color of the border or whatever. Now, those kinds of things make sense to us as human beings. Yeah, we can understand that. Moving left and right, up and down, changing a color. Yeah, it makes sense. Now, with things like this, this becomes so technical that it's so unusual for us to think in this way, because this is this is the sort of thing that we just have to do to make things work. So the reason I say that is because this episode is not going to cover raster interrupts in detail, every little specific detail, how we do this and whatever. Because you can do a lot of cool stuff with raster interrupts when you get super good at programming. But my point with this video is, first of all, tell you what raster interrupts are, and at a basic level, how they work. So we're not going to go into detail with the code here. We're going to look at the basic level how it works. And of course, we are also going to talk about why we have to use, or why we should use, raster interrupts. So I'm just gonna start this episode by telling you this to set your expectations accordingly. So we're not gonna go into detail, but we are going to use raster interrupts in our game. And we're gonna take a look at why. Now, what are these raster interrupts? Well, in order to understand that, we need to remember that we're talking about old school televisions, right? CRT TVs. Now, the way CRT TVs work is that there's a tiny little dot of light that travels across the screen at a fantastical speed from left to right, goes over here, left to right, goes over here, left to right, and it travels down the screen like that from left to right. For every time it goes from left to right, it goes down a little bit and goes across, goes down. So the screen is drawn like that at a fantastical speed. And let's take a look at this now. So when we're when we're programming for the Commodore 64, there are two different TV standards. We have NTSC, the standard that's used in North America and Japan, and then we have PAL, which is Europe and a lot of other countries. I can't remember exactly. Australia as well. But anyway, we have these two different TV standards. Now for the NTSC standard, that television is updated at 60 Hz, which means 60 frames per second. For the PAL standard, it's 50, so it's 50 frames per second. Now, again, let's not go super into detail here, but it means that there are two different standards. So what's important here is how this works with the Commodore 64. So the screen is updated 50 or 60 times a second based on what TV standard you have. So we don't need to go into any detail about that, but it's important to know about that. So now, what does that have to do with raster interrupts? Well, before we do that, I want to show you a tiny little clip from some YouTubers called the Slow-Mo guys. Now I asked them if we could use a little clip, but they never responded, so I'm gonna be a little cheeky and I'm gonna show you just a few seconds, and hopefully they are okay with that. So let's take a brief look at a video from them to show you exactly how the TV is updated. Let's take a look at that now.
Slowed all the way down to 2500 frames a second, you can now differentiate each individual frame being built from top to bottom.
So hopefully the slow-mo guys aren't mad at me now. But the point of showing you that is to give you a really good mental picture of how this actually works. So we're not seeing, with a human eye, we think we see a complete picture, but in reality, it's just that line or that dot of light moving across the screen so fast that we think we see a complete picture. So why is that important now? Well, that little row of light that we can see, that's what we call a raster line. So now, in order to understand what raster interrupts are, let's take a quick look at what interrupts are. So what are these interrupts? Well, it's a computer term, and it's not something just for the Commodore 64. It's something that has to do with computers. So let me read a definition here from osdev.org, what they say interrupts are. It says, interrupts are signals from a device, such as a keyboard or a hard drive, to the CPU, telling it to immediately stop whatever it is currently doing and do something else. For example, a keyboard controller can send an interrupt when a character was pressed. So, this is, as I said, this is something that has to do with computers, and it is something that occurs. So it's an interrupt to the CPU. The CPU is working on something, but something happens, and the CPU is interrupted. So that's what we're going to take a look at now. How the raster line on the TV can interrupt our Commodore 64 CPU. So when it comes to rasterrupts on the Commodore 64, remember this raster line. So what we can do, we always know where the raster line is, because we can read it from a memory address called D012, D1012. That memory address contains the current raster line. So what we can do, we can say when the raster line has gone down to, let's say, raster line 200. Whenever the raster line reaches line 200, then we're going to trigger an interrupt. So let's take a look at that now. So here I have made a short example of raster interrupts on the Commodore 64. So start our program as normal, but here in my main, under my main label, I have jumped to subroutine, set up raster interrupts. Alright, but then we have our game loop down here, and right now it's just an empty loop, right? It doesn't do anything. But if you look down here, we can see that I have imported a file called interrupt.asm, and that's obviously where this subroutine is located. So let's take a look at interrupt.asm. This is it. Now, this is what I was talking about in the beginning. I'm not going to go into detail. And if this was a classroom situation, I would just give you this file and tell you how to use it. Because now in the beginning, I don't expect you to create your own, or so in one way or another you have to do that, right? But there are so many memory addresses here, and ones and zeros. So at the very beginning now, the important part is that you understand what this is and how we use it and why we use it. So I'm just quickly gonna go through this to show you. And in fact, like I told you last time, at the end of the course you will get the entire source code and the interrupt setup will be there. But we need to know at the conceptual level what's going on, because at some point you will have to make this yourself. But there are a lot of examples online that you can look at. So we start off by a new mnemonic that we haven't seen before. SEY. It's disable interrupt requests. So raster interrupts aren't the only interrupts happening on the Commodore 64. So there are other interrupts as well. Now, we're not going to go into detail on that either. But when we're saying SEY, we say disable the interrupts. Because what we're going to do now is super important, and if we're interrupted in the middle of setting up this thing, then you're going to have some issues. So we don't want that. So we just say SEY disable interrupt requests. We don't want any interrupts right now. Okay, so now we come to sort of the technical part that I was talking about. Now we haven't looked in detail at the Commodore 64 hardware, but there are two chips called the CIA1 chip and the CIA2 chip. Now once again, there is a lot of stuff going on with those two chips. So let's for now just accept that we are disabling interrupt signals from the CIA1 chip, and we are disabling interrupts from the CIA2 chip. Let's just accept that for now. Then we are saying we need to acknowledge pending interrupt requests from CIA1 and CIA2. So this is what I was talking about. So moving sprites left and right, that makes sense to us. Now this gets so technical that it's hard to place it in relation to anything else. So that's why we need to not go into detail right now. The point is that now we're setting up a raster interrupts. So this is a setup routine that's going to allow us to do this properly. Now we get to a familiar address down here, or at least a little bit. We briefly looked at it last time. It's D1011, the one that I called Screen Control 1. Now we saw that there was some stuff going on in there with the different bits, and we didn't take a close look at the 7th bit, so bit 7 on this one. But here it says clear bit 7, since we are not using raster interrupts past raster line 255. Now, what on earth does that mean? That's strange, right? Well, now we need to take a look at another thing. So here I am at this great web page called Dustlayer.com. Now he has made a great picture for us to show the Commodore 64 resolution. We may have looked at this before, I'm not sure. But anyway, the important part here is that we know that this area is 320 pixels across, this background area, and 200 pixels down like that. So we know about this background area, 320 by 200. We've seen that before. But that's not the entire screen. So first of all, that's just this background area. There's also this border area. That's outside this 320, 200. And as you can see, this is 284 and 403 wide. But if we look at the entire screen, it says 312 from top to bottom, 504 across, which means that we are operating with numbers like in this case 284 here, 312 here. So we are operating with numbers higher than 255. Now, the reason the way Commodore's engineers handled that was the following. Now, by using my calculator here, I can show you what I'm talking about. So how can we deal with numbers higher than 255? Well, normally we can't. But if you do a special little trick, you actually can do that a little bit. But this is not something I recommend doing in your code, because this can get a little messy. But the Commodore 64 engineers designed this into the CPU, so we don't have to worry about it. But my point is, how can we go beyond 255? Well, let's take a look at the bits here. We know that an 8-bit number, that's 8 bits, right? So I'm going to flip all these bits to 1. So I'm going to flip this, 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 and so on. So I'm flipping all the bits here to 1. And when I flip all the 8 bits, we end up with 255. What if I try to flip this next bit? 511 or 512, since we're counting from 0. So just by adding one more bit here, we can double the number from 256 to 512. Now, the reason I said it was a little messy is that you can technically do these sort of things by combining memory addresses and stuff like that, but I don't recommend starting with that now in the beginning. So, but anyway, we have this number 512 now, which is going to be okay now because we have 312 here, 284 here, so now we can deal with this. So, why am I talking about this now? Well, we might want to trigger the raster interrupt anywhere on the screen, and in fact, I don't recommend triggering the interrupt right in the middle of this background area, unless you know exactly what you're doing. So what I like to do, I like to place my interrupt here at the very bottom, or at least after the screen, the background here. And the reason why is I'm going to show you that in just a minute. But for now, let's get back to the code. So we looked at the reason why we have this 8th bit. So again, let's not worry too much about that for now. But I said we need to trigger what raster line we want the interrupt to happen at. Also, where do we want the raster interrupt to trigger? Here I said I want the raster interrupt to be triggered at line 200. The raster line to trigger a raster interrupt at. So I load that number and I store it into D012, so D1012. This memory address is the memory address that holds the current raster line. So if we read that memory address, then we get the current raster line, but if we write to it, then we say what raster line we want to trigger the raster interrupt at. So it's different if you read or write to it. Then here we get to something else. Now, we haven't looked too much at this, but we have talked about low byte and high byte. So if we have a memory address like this, we know that we can split it into two and we get the low byte and the high byte. Well, that's actually what's going on here. But now I'm using this. So these symbols. This means when we use it this way, it says that's the low byte. So by using this, I say I want the low byte of this. When I use the symbol the other way, it says I want the high byte. Now, in addition to that, I use a hashtag in front of it. So that means that if we go down here, there's a label that says IRQ. Remember, these kinds of labels are memory addresses. So if we are specifying a variable or a subroutine or whatever, if we use a label like this, it's a memory address. So that means that instead of IRQ here, that's actually a memory address. So, and I have specified a routine under that. So let's go back here. What am I saying? Well, as we know, memory addresses, those are 4 digits, right? So we need to split them into 2 so we can handle them properly. So that's why this IRQ thing is split into 2. So I'm saying I'm going to take the low byte of this memory address and I'm going to take the high byte of the memory address, and I'm going to store those into 2 memory addresses that's set up by the Commodore 64. So here I say I'm taking the low byte of the address for our interrupt routine. So I made an interrupt routine down here. This is my interrupt routine that I made. It's down here. So I say the low byte of that routine, store that in 314. The high byte of that routine, store that in 315. So we looked a little bit at these sort of things when we were dealing with a 0 page. So we know that we can combine 2 numbers to create a memory address. And basically that's what's going on here. Now, we're not using 0 page, but this is something that's handled by the Commodore 64 itself. But we need to specify where our interrupt routine is located. So we just tell the Commodore 64 at these specified memory addresses. Where is the low byte? I have to give the low byte and the high byte of where that routine is. My interrupt routine. So I'm telling the Commodore 64 where my interrupt routine is. Then again, some sort of memory address here. I'm just saying by setting bit 0 to 1 here, I'm enabling the raster interrupts. So let's accept that for now. And finally here I said CLI, clear interrupts. So that's going to mean, all right, now we're done with this setup. Now we can enable interrupt requests again. So we tell the Commodore 64, okay, we said disable interrupts. Right now we don't want any interrupts. So we disable all interrupts, then we set up our raster interrupt. When we're done with that, we say, okay, we're done. So now we enable interrupt requests again, so the Commodore 64 can work as normal. CLI, clear interrupts, enable interrupt requests. And then I just say RTS, which is return from subroutine, which will bring me back here. So this whole thing was in a subroutine here called setup raster interrupts. So what that thing did was to set up my raster interrupts, just so I can use it later. But now I just set it up, and I also, in this setup routine, I also enabled raster interrupts by using this memory address. So now my raster routine is set up. What does that mean? Well, it means that now this thing is in place. So if I'm on a PAL machine right now, every 50 times a second, 50 times every second, my interrupt routine will be triggered. It will be triggered at line 200. That's what I specified here. I want my raster interrupt to be triggered at line 200. So every time the screen is updated and the raster line gets to line 200, then my interrupt routine is triggered. Then the CPU stops whatever it's doing, and what happens now? Well, now the interrupt routine is run. So now this IRQ routine is done. So let's take a look at that. Here is my interrupt routine. So it starts up here and it ends down here. So what does my interrupt routine do? Well, the first thing we need to do is to acknowledge a raster interrupt. That's done with bit 0 here, setting 1 to bit 0 at a memory address D1019. So we need to acknowledge that, alright, we are inside an interrupt routine now, so we have acknowledged that. Now, here comes whatever I want to happen in my interrupt routine. I've done something really simple now, just to show you how this works. Now I say decrement D020. So the border color, change the border color with, decrease the border color number. So it's going to change the border color to whatever color code was below whatever I had before. Let's say we change the border color. Okay, then I have a short little loop here. It's just a delay loop to waste a little bit of time. So I waste a little bit of time here. Whoops. Just waste a little bit of time in here. And then here I say decrease the border color. I waste a little time and then say increase the border color. So go back to what it was. So at a short period of time, very short period of time, the border color is going to be a different color. I change it here. I wait a little bit here, just to wait a little bit, and then I change it back. So if we had color code 1 here, and we say decrease it, then I'm so sorry. We would go from color code 1 to color code 0. We decrease the color code. And then we wait a little bit, and then we get down here, increase. So we go back from 0 to 1. So we're just changing the border color down and up. But in the meantime, we wait a little bit here. Hopefully that made sense. But here's another thing. So a viewer made a comment a while back, and he said you don't need to use compare with 0, and he's absolutely right. When we are using CPX, CPY, or compare, if we are using those compares, compare X, compare Y, or normal compare, CMP, with 0, we don't have to write compare with 0. So whenever you're comparing with 0, you don't need to write compare with 0, because of the how the 0 flag works. Let's not go into detail about that right now, but just remember that whenever you're comparing to 0, you don't have to actually write compare with 0. So in this case, I load X with 250, I increment X, so it's going to go up a little bit, and we increment X with 1, so from 250 to 251, and a branch if not equal, so if the carry flag is not set, we go back here. So anyway, it's just a little trick to, you'd never have to write compare with 0. But anyway, this is my little wait loop. Change the border color, wait a little bit, change the border color back. Then we get down here to another special memory address. This a special memory address, as you can see, is located in the kernel. Now, it's a special routine there, and by the way, notice that we're jumping to that routine. So it's not a jump from subroutine, jump to subroutine. It's a normal jump. What this routine does is it's called the kernel interrupt return routine. So it's gonna bring us out of this raster interrupt routine. It's gonna bring us out of that, and it's going to restore our registers: X register, Y register, accumulator, and CPU flags. It's going to because all of those things might get corrupted in here. So before we go into any more into detail now, let's just take a look at how this works. So remember now, the point is that now I've set up my raster interrupts to trigger at line 200. So whenever the raster line reaches line 200, then I trigger an input, and then I trigger a raster interrupt. What does my raster interrupt do? Well, it does whatever I specified here under IRQ. That was my interrupt routine, right? I specified it here. So every time the raster line reaches line 200, this is going to happen. The CPU is going to stop for a little bit, doing what it normally does, my normal code. So my normal code over here, because this is running all the time. But when the raster line reaches line 200, it's going to stop here and perform this. When that's done, it's going to go back here and continue what it was doing here. So right now we're not doing anything here, but let's see if this works now. So I don't know if you can see anything here, but something is actually happening. What's happening? Well, let's take a look here. We have our border around here, but maybe you can see this thin little green line here. This is where I'm changing the border color and changing it back with this little wait loop in the middle. So by doing that here in the interrupt, now we reach line 200 and the interrupt routine is triggered. When it's done, it goes back to the normal routine, continue as normal. But in this short period of time, short moment in time, we are changing the border color. So that's what's happening in here. Now let's see if what happens if I increase if I make my delay loop last a little bit longer. Let's see if we can see a little different now. So difference. So instead of loading X with 250, which will make it run only 5 times, now I'm saying load X with 0 instead, so it will run 255 times, my delay loop. Alright, let's see if we can see any difference now. Now I changed the border color, I wait a little bit longer, and then I change the border color back in my interrupt routine. Let's see if we can see any difference now. So now you can see that my interrupt routine, I'm waiting a little bit longer between changing the color and changing it back. So that period of time shows here. So this is where I'm changing the color. Now I'm waiting, and now I change it back. That's what's going on here. So this is a very simple example to show you how raster interrupts would work. Now I'm changing the border color here just as an example, but we need to do other stuff in the raster interrupt routine, unless of course you want this. So what do we do? What do we normally do? Well, what we normally do is anything that needs a stable frequency. So, for example, maybe the best example, playing music in your game. Now, it's almost like I would say you have to do it in your raster interrupt routine, because music is so dependent on having a stable beat. Boom, 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 boom. So we don't want the speed of the CPU to go up and down and affect how the music sounds, right? Now the raster interrupt, that's maybe one of the most important things here. It's stable. We know that it runs for my PAL machine here 50 times every second. This routine is triggered at line 200. So that means that we have a stable beat. So it's perfect for playing music, for example. For my code over here, my main code, now this is the interrupt routine, this is my main code. Over here, how fast things are happening might depend on whatever is going on in my code. So, and depending on how I program things. But if I am not careful with timing, then sometimes things can go really fast, sometimes things can go really slow. And especially if you have played games on the Nintendo Entertainment System, a lot of people call it slowdown. So if there is a lot of stuff happening on the screen, things really slow down a lot. And that's because the CPU has so much to do. So that's not a stable frequency, right? So if you were going to play music in that environment, it would be, sometimes it would go really fast, sometimes it would really slow, and the music would sound very strange. But if we play the music here in the interrupt routine, it's a stable beat, bum, 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 bum. So that's why it's such a good idea to play music in your raster interrupt routine, because we know of this stability. So the code is going to happen, raster interrupts 50 times every second on PAL, 60 times every second on NTSC. So hopefully you can see the point that that's one of the uses of a raster interrupt routine. Now, another reason that I like to use it for is updating sprite positions. So we looked, when we were moving sprites around the screen with our joystick, we could see that if I just say increase the X position or whatever, the sprite was moving super fast in any direction, and it was sort of stretched like that. Because the screen was updating at the same time that the code was moving the sprite. So as I said, we weren't in sync with the screen update when we were moving the sprites. So what I do, I update we need to update the sprite positions in our main code, but not directly to D000, so the memory address for the X position, for example, or Y position. So I just say, instead of updating them directly, I have think of it as a variable. So I have a variable, put my positions in there, and then when the interrupt routine is triggered, then it's gonna read that variable where I stored where the position should be, and this interrupt routine updates D000, so the position of the X position, or D001, the Y position. So the actual X and Y position is updated here in my interrupt routine. So that's gonna mean that the actual movement of the sprite is gonna be in perfect sync with my screen update. So that's gonna mean that my sprite won't be stretched out like that, moving super fast like that, but we are going to update sprite completely in sync with our screen update. So hopefully that made sense. So as you can see, like I said in the beginning, this is such a technical topic that it's hard to cover it in detail in a video like this. Now I want to tell you another thing. So we have looked at how we could set up an interrupt routine like this. So this interrupt routine is triggered at line 200. Now it's also possible to have multiple interrupt routines like this. So I could have this could be IRQ1 and I could have IRQ2 and so on. Now why would you do that? Well, again, there could be several reasons, but there are games that have parallax scrolling, so the background scrolls at different speeds. So let's take a little look at an example where that's going on. So let's take a look at this game, Rim Runner. So as you probably could see, the background was moving at different speeds, so parallax scrolling. And that could be achieved by having multiple interrupt routines like this. So again, we're not going to be doing scrolling, but it's probably good that you know about these things. So you could have different interrupt routines and do scrolling at different speeds in those different routines. Okay, so we have talked a lot about raster interrupts, and like I said, I wasn't going to cover this in detail. Hopefully, again, I got everything right. But this is the sort of thing that you might want to do some extra reading on, and I'm going to leave a few links in this video description so you could read more about this in detail. But my point with this video was to show you the concept, what raster interrupts are, how they work at a conceptual level, and why we use them. So hopefully I got the point across. So I think we'll say that that's enough for today, and as I said, if you want to do some more reading, then I'm gonna leave some links in the description field. Alright, well, that's it for now, so I'll see you next time. Bye bye.